So how do I interpret this scatter plot now that I've made it? We're going to look at some basic data analysis strategies from chapters 1 and 2. What we really want to do is we want to look for patterns. We want to look for trends. So in any scatter plot, we're looking for the overall pattern or any striking deviations from the pattern. Deviations mean values that are far away from the pattern. You could also think of that as like outliers, be those positive or negative outliers. Then what we want to do is describe the overall pattern by its direction, right? We're going to talk about that. It can be positive or negative, right? What form it takes on, and the strength of our correlation. That's going to be our correlation coefficient, which is, you guessed it, what I'm talking about in this video. Lastly, an important kind of departure, like I said, is an outlier, right? It just falls outside of the overall pattern of the relationship and can sometimes affect the correlation. So maybe make sure you're keeping like a close eye out for outliers. So let's talk about the types of correlation. Okay, so we've got positive correlation. So this is when the values of y tend to increase with increasing values of x. So it looks like it's got like positive slope. Let me change colors. So if we were thinking back to like college algebra, when we first graph lines, right? Like we've got some positive slope, right? And this line C here, this shows like a positive, this is C. Here's A, B, C. I guess I didn't label them. Our correlation becomes stronger because our values get closer and closer to this like imaginary line of best fit that I'm drawing right now. We will learn how to calculate those. But right now I'm just drawing them. And this is perfect correlation, right? When R is 1. R is our correlation coefficient. I'm going to dive more into that later and how it's calculated. But for right now, I wanted you to see what positive correlation looks like. If we've got positive, we've also got negative. So here's negative correlation, T, E, F, right? So we can kind of see, oh yeah, this kind of looks like it's going downhill. I want us to get like a gut instinct for correlation first, right? Here's what my lines might kind of look like. Notice that our correlation gets stronger, right? It gets more negative, but stronger as it proceeds from left to right, from D to F. And my values, what they are is they're getting closer and closer to this like best fit line, like they're less spread out. So we can have positive correlation, we can have negative correlation, we can also have no correlation. That could be a thing too, right? Can we see any like trend line that's better than any other in this graph? No, not really. And it's also important to note that like correlation doesn't mean slope. Like I know like this line right here, this one has a slope of 0. Again, thinking back to college algebra, not trying to traumatize anybody. But it just kind of appears that there's no relationship between my x values and my y values. Aside from that, and I don't know if we're going to discuss that much in this class, but we can have a nonlinear correlation. So that means my graph just doesn't look like a line, non-linear, right? This would be more of like a quadratic, a parabola. You could also have graphs that like go like this, right? So we could have non-linear correlation. So here's a quick summary of the types of correlation. So with positive correlation, both variables increase or decrease together. Negative correlation, the two variables tend to change in opposite directions. There's no correlation, or you could have a non-linear relationship. So how do I measure that strength of correlation, right? I was telling you, oh, look, it gets stronger as the values get closer and closer to that like imaginary line I've been drawing in. But for that, we're going to need our correlation coefficient, R. So we measure the strength of a correlation, because we are all now statisticians, with a correlation coefficient, and we call that letter R. So our correlation coefficient, again, is not slope. Warning, not slope. I forgot how to spell slope, but it's not slope. So our correlation coefficient measures the strength of a relationship, and it can go from -1 to 1, right? It's positive if I've got positive correlation, so my slope does look like it's going uphill. It's 0 if there's no correlation. And then it's negative if my correlation is negative and it's going like downhill, but from -1 to 1 only. So let's say I have positive correlation. So values of R that are close to 1 means strong positive correlation. And positive values closer to 0, that's going to give you weak correlation. We want strong correlation. We want like strong lines. Perfect correlation, not really going to happen. Not with, randomly produced data. But we can get pretty close, we can also have negative correlation. If my value is as close to -1 as possible, that means I've got like strong correlation. And as I get closer and closer to 0, we'd call that weak correlation. Anything over like a 0.8, either negative or positive, I'd consider like pretty strong, but less than that, not really great correlation. We're going to want to ignore that. So a couple properties of R. There's positive correlation. If we've got perfect correlation, R is 1. If we've got negative correlation, my R value is between -1 and 0. -1 means perfect correlation. I'm kind of repeating myself a little bit in these slides that you have access to. So how do I measure? How do I find this R? It's like, okay, Dr. Miller, you told us R is our correlation coefficient. That's great. How do I find that? So before I show you this formula, please know, friends, we are not going to calculate this by hand, right? So like I said, R measures the direction and strength of our linear relationship between quantitative variables. So if I have all my X and Y, right, values for however many pieces of data I have in the data set, so we could say like our first 2 pairs, like we're plotting, remember we had a data set, we're plotting pairs, each of those pairs would be like X, Y, right? Ordered pairs, again, college algebra trauma, I know. And we also calculate the standard deviations and our mean. The formula for R is this. It's not so great. Here it is in a shorter form. But like I said, we will not do this by hand. So what it's doing though is it's taking each individual X value, subtracting the mean of that X value of our explanatory variable, and dividing that by our standard deviation of X, multiplying that by each Y value, subtracting the Y mean, dividing by the standard deviation mean, multiplying those together, adding them up with the summation symbol, and then multiplying the whole thing when we're very done by 1 over our sample size minus 1. But we aren't going to do this by hand. We're going to do this in R. And we'll talk more about that in our next video.